Noir plasma chrome bleed. Unlocking knowledge, inspiring innovation, empowering curious minds.
This website makes learning so easy. I found all my resources here.
Like what you share.
Welcome to this explainer. Today, we're taking a massive leap way beyond the basics. We are going to unpack how physicists actually upgrade fundamental quantum mechanics into an advanced, incredibly powerful mathematical toolkit. This is the toolkit that allows them to calculate the often chaotic, super complex nature of reality itself.
So, let's dive right in. We have to start with a pretty massive problem. Basic quantum equations, like the exact clean solutions you might see in an introductory physics class, they're fantastic if you're dealing with a solitary, perfectly isolated hydrogen atom, but they utterly fail when real-world variables crash the party. I'm talking about electric fields, magnetic fields, and the extreme speeds of relativity. The universe is messy, and our math absolutely has to reflect that messiness without just completely breaking down.
Here's our roadmap for fixing those failures today. 1. Tweaking reality. 2. Bridging classical and quantum. 3. Time, lasers, and light. 4. Crashing particles. 5. Relativity meets quantum mechanics. And finally, 6. The grand quantum synthesis. We're going to take you from minor mathematical tweaks all the way to synthesizing a complete model of the universe.
Section 1. Tweaking reality with perturbation theory. First up on our journey, we tackle how to handle small, pesky disturbances in atomic environments, all without having to throw away the foundational math we already know.
This brings us to perturbation theory. Think of it kind of like calculating the swing of a perfect pendulum in a vacuum. Once you have that exact mathematically pure swing figured out, you really don't want to start entirely from scratch the second you take that pendulum outside. Instead, you use perturbation theory as a specific mathematical tool to just add a slight breeze to your existing equation and see what happens. Physicists use strict mathematical rules, like the Kato-Relic theorem, to ensure that when they add these little tweaks, the whole equation remains stable and doesn't just spiral out into infinite nonsensical garbage.
So how do we actually apply these tweaks in real life? Well, this toolkit is exactly how we explain the real fine structure of atoms. You see, a real electron doesn't just orbit cleanly. It moves at relativistic speeds, which actually changes its kinetic energy mass. It also has a magnetic spin that reacts to the electric field of the nucleus, a phenomenon we call spin-orbit coupling. And finally, there's the Darwin term. Because of quantum uncertainty, the electron is constantly rapidly jittering back and forth. It's a phenomenon famously called Zitterbewegung, which literally smears out the electric field it feels. By mathematically stacking these three corrections, we get an incredibly accurate picture of the real hydrogen atom.
Section 2. Bridging classical and quantum. Next, physicists needed a mathematical bridge between the smooth, predictable classical world we see every day and the strange, jumpy, discrete quantum realm of the microscopic.
Semiclassical approximations act as that exact bridge. But it gets tricky because we actually have to use totally different mathematical tools depending on how the system is behaving. If a system is integrable, meaning it's stable and predictable, we can just use standard methods like EBK quantization. But if we're dealing with non-integrable systems, where those predictable structures are totally destroyed, we enter the wild realm of quantum chaos. Suddenly, the classical orbits become dense, unpredictable, and incredibly unstable.
So how in the world do we find quantum order inside all that classical chaos? Well, for those chaotic systems, we rely on something called the Gutzwiller trace formula. Martin Gutzwiller proved something just incredible. Quantum spectral densities actually emerge from the constructive interference happening along highly unstable classical orbits. Basically, even in a system that is classically chaotic, the quantum waves overlapping along those wild paths create measurable, distinct quantum states.
It's a stunning, beautiful connection between chaos and order.
Section 3. Time, lasers, and light. Let's explore how all this math builds into the physical technology we use every single day, specifically looking at how quantum mechanics reacts to the relentless march of time and interacting light waves. To figure out how particles transition between states over time when they're being bombarded by radiation, we use Fermi's golden rule. When an atom absorbs or emits light, it transitions into a continuous spectrum of states. This elegant formula is essentially an absolute cosmic accountant. It allows physicists to calculate exact transition probabilities and rates, while strictly enforcing that the total energy before and after the transition remained entirely conserved. And you know what? This specific math is exactly what makes the lasers at your grocery store checkout or inside your fiber optic internet actually possible. Lasers rely on a fascinating four-step process called population inversion. First, you start at the ground state. Then you pump the atoms full of energy up to state 3. You let them decay slightly to a more stable state 2, and then finally trigger them to drop down to state 1. By stacking way more atoms in that upper state than the lower state, which is an artificial inversion of normal thermal equilibrium, stimulated light emission massively outpaces absorption. The end result? A perfectly coherent, focused beam of laser light.
Section 4. Crashing particles with scattering theory. Let's shift gears now. What happens when physicists just want to know what a target is made of? Well, they smash particles into it. Let's look at the math behind scattering theory.
When you shoot a tiny particle at a complex target, calculating exactly how the wave behaves inside that target is, well, practically impossible. So, physicists use a brilliant mathematical cheat code known as the firstborn approximation. Instead of trying to map out the completely unknown internal wave function of the target, this approximation just pretends the internal wave is an undisturbed plane wave. And surprisingly enough, for really fast, high-energy collisions, this cheat code works beautifully to calculate exactly how the particle is going to scatter.
Now for slower collisions, we use something called partial wave analysis. Imagine throwing a stone into a calm pond and watching the ripples hit a submerged rock. By tracking how those ripples shift after they hit it, you can learn about the rock underneath. In quantum mechanics, a positive phase shift means the target's potential was attractive. It literally pulled the incoming wave in. A negative phase shift, on the other hand, means the target was repulsive and pushed the wave away. By measuring these tiny phase shifts, we can actually mathematically reconstruct the invisible forces at play.
Section 5. Relativity meets quantum mechanics. This is the absolute climax of our quantum journey. What on earth happens when particles move so incredibly fast that we have to marry the weirdness of quantum mechanics with Einstein's special relativity?
Early attempts at this marriage, like the Klein-Gordon equation, literally ended in mathematical disaster, producing impossible negative probabilities. To solve this, the brilliant physicist Paul Dirac completely revolutionized physics. He formulated the Dirac equation by introducing some incredibly complex math called 4x4 Clifford algebra matrices into a new, fully covariant wave equation. He didn't just tweak the math here, he fundamentally upgraded the dimensional structure of how we calculate reality.
Not only did Dirac's math completely fix the probability issues, but it did something absolutely mind-blowing. The math accidentally demanded the existence of negative energy states. To explain this away, Dirac proposed what he called hole theory. He suggested that an infinite, invisible sea of electrons exists everywhere around us. If an electron is somehow missing from this sea, that empty hole would act exactly like a particle with a positive charge. Without meaning to, Dirac had literally just predicted the positron. He proved the existence of antimatter using only a pencil and paper years before anyone ever discovered it in a lab.
And as a brilliant bonus, there was another massive mystery at the time. Electron spin had this weird magnetic factor, called the G-factor, that earlier physics just couldn't explain. But if you take the non-relativistic, slow speed limit of Dirac's new equation, the math naturally spits out the exact number 2. It didn't have to be forced in. The precise magnetic moment of the electron was simply a beautiful, perfectly natural consequence of uniting quantum mechanics with relativity.
Finally, Section 6, the grand quantum synthesis. Let's move to our last section and see how all of these incredibly complex frameworks actually build into one single, cohesive structure of reality and space-time.
The absolute crucial takeaway here is that these aren't just isolated random equations. They form a deeply interlocking framework. Kato-Rillich operator bounds guarantee that our mathematical models remain perfectly stable when we poke at them. Semiclassical models bridge that weird gap across phase space from the macro down to the micro.
Scattering theory lets us test these bounds in continuous spectrums. And the relativistic math of Dirac guarantees that when things speed up to the speed of light, observable reality, like antimatter and spin, emerges flawlessly.
So we've built this beautiful, robust mathematical toolkit that explains almost the entire microscopic universe. From the lasers in our daily technology all the way to the antimatter floating in the cosmos, the toolkit works. But it leaves us with one profound, lingering question to ponder. We have successfully merged relativity, chaos, and quantum mechanics, but how do we calculate reality when the immense, crushing force of gravity finally enters the quantum realm? That is the next great frontier. Thank you so much for exploring the Physicist's Toolkit with me today in this explainer.
Like what you shared.
This website makes learning so easy. I found all my resources here.
Noir plasma chrome bleed. Unlocking knowledge, inspiring innovation, empowering curious minds.